Uh, good afternoon, ladies and gentlemen. It's a good afternoon here in Los Angeles, California. My new topic this afternoon is it's almost the last part of differential calculus. Actually, what I will be discussing now will be the last derivatives under differential calculus, that is derivative of inverse hyperbolic functions. Derivative of inverse hyperbolic functions. I think that's the last part of differential calculus. For us to go to integral calculus, we must now have to know this. We are almost in the photo finish of differential calculus. Okay, to continue this afternoon, I will now try to derive the first two equations for taking the derivative of inverse hyperbolic functions. We are now through with the derivative of hyperbolic functions. What we study this afternoon is the derivative of inverse hyperbolic function. It is the reverse of that one. Okay. I will check my camera. Okay, let's proceed. The number one formula under inverse hyperbolic functions, that is under derivative. I will give you the first two formulas. The derivative with respect to x of inverse hyperbolic sine of u equal to 1 over the square root of u square. This should be plus 1, I forgot, plus 1, times du dx. That's a general equation. For as long as you are taking the derivative of inverse hyperbolic sine, this is the formula. So if they give you a problem under inverse hyperbolic, to differentiate inverse hyperbolic sine, this is the formula. I will repeat it before I will proceed with the derivation. The derivative with respect to x of inverse hyperbolic sine of u, where u could take any function, could be algebraic, trigonometric, or exponential, or logarithmic, okay, is equal to 1 over the square root of u square plus 1 times du dx. Okay, let's proceed with the derivation. We let y equal to inverse hyperbolic sine of x. For the meantime, it is not u. We place it as x, okay? Take the derivative now of both sides. The derivative with respect to x of y equal to the derivative with respect to x of the right hand side. The last time around, we derived the equivalent of this in terms of natural logarithm. That's why before I proceeded with the derivatives, I give you the formulas on how to take the derivative of the inverse hyperbolic. And under inverse hyperbolic sine, the equivalent of this under natural logarithm is the natural logarithm. Just try to recall what we studied the last time around. The natural logarithm of the quantity x plus or minus square root of x squared plus 1. The equivalent of this is this one in terms of the natural logarithm. That was the last topic the last time around. Okay, let's proceed with the differentiation. It's an easy matter now because we know how to differentiate natural logarithm, right? Because without knowing this, without knowing that inverse hyperbolic sine is this, you cannot differentiate this one, right? That's why we study first the equivalent of inverse hyperbolic sine up to cosecant the last time around. That's the importance of that topic. Okay? Let's proceed with the differentiation. The derivative with respect to x of y is just dy dx. And under the natural logarithm, what we studied under natural logarithm, if you take the derivative of any natural logarithm of any function, it is just 1 over u times du dx. Okay? That was under natural logarithm. This falls under the natural logarithm of u, where u contains two functions. It is x plus or minus the square root of x squared plus 1. So if we just follow this, it will be 1 over x plus or minus the square root of x squared plus 1. This is u. Okay? Times the derivative with respect to x of u. But what is u? It is x plus or minus the square root of x squared plus 1. Okay? So we will just rewrite this one, then proceed with the derivation of this. Sum and difference. Easy, right? What is the derivative of x with respect to itself? It is 1. What is the derivative of x squared plus 1 square root or raised to the 1/2? It falls under the power formula. This one. It falls under the derivative of u to the n. And under algebraic differentiation, it will be nu raised to n minus 1 times du dx. That's why we started with algebraic differentiation, because in the last part, we needed those. Right? So we'll just follow the derivative of u to the n. Nu raised to n minus 1 times du dx. What is n? N is 1/2. Okay? Times x squared plus 1, decrease in power by 1. What is 1/2 minus 1? It is 1/2, but it's negative. Right? Because 1/2 minus 1, 1 is greater than 1/2. So the sign will be negative. 1 minus 1/2 is minus 1/2. 1/2 minus 1 is minus 1/2. Times the derivative of the term inside. It's again an algebraic function. Right? Power formula again. So, nu raised to n minus 1. So, 2 times x raised to 2 minus 1, or just simply x, times 1. Plus the derivative of 1, it is 0. This is actually, the continuation of this is plus 0. I didn't place it anymore. The board is too short, right? I just simplify it. But at least I explain it. Why there is no plus 0 over there. There should be plus 0. Space constraints, right, guys? Simplifying this is now equal to 1 over, we just rewrite the first one. For this one here, it will be, if you try to eliminate this negative power here, you bring it down, okay? So what will come out is just simply on the numerator is 2x, it is this. This will go down, so it will now be x squared plus 1. Actually, that is raised to the 1/2. If you bring it down, this negative will become plus. So what will come out is just 1 plus or minus 2x over 2, the square root of x squared plus 1. The simplification of this by eliminating the negative power. Just bring it down on the denominator. Okay? That's algebra. These two here cancel with this. So if you try to simplify this one, it will become the square root of x squared plus 1 times 1 is the square root of x squared plus 1. There is a remaining term on the numerator to be x. I just reoriented or rearranged. I write this first before this one. So x plus or minus the square root of x squared plus 1 all over the square root of x squared plus 1. And luckily, this term here is same as this. So actually we can cancel this one. The operation is multiplication. You can make cancellations, right? Oh, that's an intelligent solution. So what will remain will be 1. Okay. This will now be 1. Okay. 1 times 1 is 1. What remains on the denominator? This is 1 also after the cancellation. So 1 times this square root is the square root of x squared plus 1. It's now in its simplest form. If we now try to bring out the general formula, if we now try to replace x by u to be more general, where u could take any function, algebraic, trigonometric, exponential, logarithmic, anything, to be more general. The derivative with respect to x of inverse hyperbolic sine of u is 1 over the square root of u squared plus 1 times du dx. That's the general formula number 1 for taking the derivative of inverse hyperbolic sine of any function. That's number 1. Easy, right? Because the last time around we derived the equivalent of inverse hyperbolic functions. Because without recalling those, you cannot differentiate. That's why I'll give you first the requirement before we proceed with the differentiation. Because without knowing those equivalents, you cannot differentiate. Okay, I will give you formula number 2 under inverse hyperbolic. Formula number 2 is inverse hyperbolic cosine of u, the derivative. I place it here, it should be 1 over the square root of u squared minus 1 times du dx. Okay, let's try to bring out the derivation of this. Same as the first one. We let y equal to inverse hyperbolic cosine of x. It's not hyperbolic sine, we are done with that one. We are on formula number 2, okay? Hyperbolic, inverse hyperbolic cosine. Okay? Y is equal to the natural logarithm of the quantity x plus or minus the square root of x squared minus 1. Where did I get this? Got this? It was the subject matter the last time around. Right? The equivalent of inverse hyperbolic cosine is the natural logarithm of the quantity x plus or minus the square root of x squared minus 1. Don't argue on this one with me because I give you the derivation of this, okay? And I am saying now that the inverse hyperbolic cosine is the equivalent of this in terms of natural logarithm. It should be natural logarithm of the quantity x plus or minus the square root of x squared minus 1. That's the importance of the topic the last time around. So I am always giving you the prerequisite on how to understand the next topic. That's what you call this systematic approach in teaching, right? Okay, let's proceed with the differentiation. Differentiate both sides. The derivative with respect to x of u, y, is equal to the derivative of the natural logarithm of this quantity. But this falls under the derivative of natural logarithm of u. Right? And under natural logarithm, if you try to differentiate, it should be 1 over u times du dx. But this u here comprises of 2 parts. Right? It is not just simply u. It is x plus or minus the square root of x squared minus 1. It depends on what is inside. Okay? It could be 1 term, 2 term, 3 term, anything. Right? But this time we got 2 terms. This u here is x plus or minus the square root of x squared minus 1. So if we try to differentiate that one by following this, okay, it is 1 over u times du dx. It is 1 all over this, okay, times the derivative of the terms inside the u. It comprises of 2 terms. It is x and plus or minus the square root of x squared minus 1. So it's looks similar from the first discussion on number 1, right? What's the derivative of x? With respect to x, it is 1. That's under algebraic differentiation. And what's the derivative of the square root of x squared minus 1? This falls under again the derivative of u to the n. That's under algebraic. If you take the derivative of the form u to the n, it should be n u raised to n minus 1 times du dx. So this should be equal to actually, I simplify this expeditiously. It should be x squared minus 1, but there is 1/2 over here, right? Raised to 1/2 minus 1 is minus 1/2 times the derivative of x squared. It will be 2x times 1, and the derivative of minus 1, this is 0. Okay? So, if we try to simplify this one and eliminating this negative sign, we bring this one under the denominator. Okay? So, what will come out will be the derivative of this is 2x over 2, the square root of x squared minus 1. Okay? Actually, this cancels. So, what will remain? I'll just rewrite the first one. Okay, this is 1, but this is a fraction. So to add it, we multiply 1 times this. It is this is square root of x squared minus 1 plus x. This is plus x. I just rearrange already automatic. Okay, all over the square root of x squared minus 1. And luckily, luckily, this term here cancel with this, right? So this will be 1, okay? This will be 1. So 1 times 1 is 1. 1 times this square root is just the square root of x squared minus 1. Okay, no magic. So to bring up now the general equation for taking the derivative of inverse hyperbolic cosine, we try to replace this x here by u. So by following this, the derivative with respect to xy, what is y? Inverse hyperbolic cosine. It is inverse hyperbolic cosine of u. I now replace x by u to be more general. So it could take any type of function, right? Is equal to, we are following this. It is 1 over the square root of u squared minus 1 times du dx. That's formula number 2. Meaning, the derivative with respect to x of inverse hyperbolic cosine of u is 1 over the square root of u squared minus 1 times du dx. Oh, it's different from formula number 1. Because formula number 1 is u squared plus 1. And formula number 2 under inverse hyperbolic cosine, it is the square root of u squared minus 1. Those are the first two inverse hyperbolic derivative equations. So the next time around, we still got 4. The inverse hyperbolic secant, cosecant, tangent, and cotangent, all inverse. It's a time constraints and it's magnetic bulb constraints. That's why I am only discussing 2 topics at one time. I think that's just more than good enough for this afternoon. So if you've got any questions, bring out your question. Okay? If you like it, click like. If you want to share it, click share. And for those who are taking up differential calculus, who are taking any type of engineering course, this is yours, guys. So if you want to subscribe to my channel, you can click subscribe. The topics on differential calculus from algebraic differentiation up to the last part, inverse hyperbolic, it's all here. So it's up to you to subscribe to my channel if you want to learn something systematic in differential calculus. Thank you.